Okay, hello everybody. Today I will continue with the Fourier transform properties, and I will start with the time scaling. So I suggest for students that have not seen yet part one of the Fourier transform to go and check and see this video before. So today I will continue with the time scaling. If I have a function ft which has a Fourier transform f of omega, so we will prove that if I will scale the function f by a coefficient a, it could be real without any restriction on a. So we will prove that the Fourier transform of f of at is 1 over the absolute value of a, f of omega over a. By definition, the Fourier transform of f of at, it is f of at exponential minus j omega t dt under the integral from minus infinity to plus infinity. So we will do the change of a variable tau equal to at. When a is positive, then d tau is equal to a dt. In fact, this relation is always verified whatever a. So now we are considering the case where a is positive. So after changing the limits, we will have dt equal to 1 over a d tau. This is why we see a factor of 1 over a appearing in the Fourier transform of f of at. So f of at will be f of tau. So we'll have 1 over a integral minus infinity plus infinity f of tau exponential minus j omega over a tau d tau. So if I will focus on this term, in the integral term, we see that this is f of omega divided by a, which is this quantity, which is multiplied by 1 over a. When it is positive, we will have 1 over a, the Fourier transform of omega of ft evaluated at omega over a. As an example, we will take ft equal to the rect function of a duration equal to t1. We know that the rect function is u of t plus t1 over 2 minus u of t minus t1 over 2. So it is a difference between two steps functions. So these results, we have already proved this relation. It means if I have any rect function of any duration t multiplied by v, it is tv, the sink of t omega divided by 2. So we are in a special case of ft when the v is equal to 1 and capital T is equal to t1. We would like to get the Fourier transform of gt, function of the Fourier transform of ft. So we are interested in getting the Fourier transform of f of 2t, knowing the Fourier transform of ft. So by using the time scaling results, we have the Fourier transform of j of omega will be 1 over a. So in this case, we have a equal to 2. So we have 1/2 f of omega over 2. With these results, we will have t1 over 2, the sink of omega t1 divided by 4. So this is our original function ft, which is a gate function existing from minus t1 over 2 to t1 by 2. And this is its Fourier transform, which is a function of the form sine x over x. Now f of 2t, we are compressing ft by a factor of 2. And we see that this duration has been reduced to half. So we will have T1 over 4 minus T1 over 4 from that side and T1 over 4 from the other side. What is happening to the Fourier transform of GT? So when we compress in time, we have like a dilatation, we have an expansion of the spectrum in the frequency domain. The time shifting or the time delay property of the Fourier transform means that if ft has f of omega as a Fourier transform, how about f of t minus t0? It means I will do a delay in time and I will express the Fourier transform of this function in terms of the Fourier transform of ft. So this is what we will prove, that the Fourier transform of a delayed function results on a multiplication by an exponential function in the frequency domain. So the proof is quite easy. So we will write now the Fourier transform of the delayed function, and we call it fd of omega, is by definition the integral from minus infinity to plus infinity, ft minus t0 exponential minus j omega t dt. So here we are applying simply the definition of the Fourier transform. And then we will take the change of variable s equal to t minus t0. Since t0 is assumed to be constant, so the differential of s will be equal to the differential of t, ds equal to ddt. As a result, I will replace the t by s plus t0 as it is seen here, and I will put the factor exponential minus j omega t0 outside because I am integrating with respect to s, and I see that the term that I have here, it is exactly the Fourier transform of ft, which is f of omega. So if I will delay in time by quantity t0, I will have the spectrum of f multiplied by an exponential function that depends on omega, assuming t0 to be constant. So this is what we will retain. Shifting in the time domain results in multiplication by an exponential function in the frequency domain. How about now if I will multiply the function xt in the time domain by an exponential function that depends on time? So this is xt, and I would like to express the Fourier transform of this, the whole function, in terms of x of omega, which is the Fourier transform of xt. So we start from the definition. Let x of omega be the Fourier transform of xt. Then the Fourier transform of xt exponential j omega 0 t is defined as usual by this integral formula. So now if I will gather the two exponential together, I will write the integral minus infinity to plus infinity xt exponential minus j omega minus omega 0 t dt. And this is by definition the Fourier transform of xt delayed by the quantity omega 0. So here we see an interesting relationship. If I will multiply in time by an exponential function, I will have a delay in the frequency domain. And if I will return back one slide before, we have seen that if we delay in time, we will have a multiplication by an exponential in the frequency domain, which is seen in the previous results. So the conclusion is multiplication by an exponential function in the time domain results in shifting in the frequency domain. Delay in the frequency domain results on a multiplication by an exponential function in the frequency domain. We have seen in my previous videos that if I have a function in time, f1 convolution f2, its Fourier transform is the product of the two spectrums of f1 and f2. So here we are seeing the inverse situation where I have a multiplication of two functions in time, and I would like to express the Fourier transform of the product in terms of the Fourier transform of f1 and f2 respectively. So we will prove that this Fourier transform, it is scaled by 1 factor 1 over 2 pi f1 convolution f2, where f1 and f2 are the Fourier transform of f1 and f2. So I will focus on the inverse Fourier transform of this convolution product, which is f1 convolution f2. So it is by definition, so I will call it I, between 1 over 2 pi integral minus infinity plus infinity, the convolution product times exponential j omega t d of omega. So what I am calculating here, I am calculating the inverse Fourier transform of the convolution product f1 and f2. And then I will express f1 convolution f2 by the definition of the convolution, which is minus infinity plus infinity, f1 of s, f2, omega minus s ds. Right. So I can reverse the order of integration. So I will put f1 of s here, ds, and I will put 1 over 2 pi multiplied by this quantity. Here I am seeing something interesting, is that this quantity, it is the spectrum of f2 delayed in the frequency domain by a quantity s. And this is exactly what we have seen before. It means that this expression, it is exactly the inverse Fourier transform of the signal f2 exponential j st. And this is what I said before. Multiplication by an exponential function in the time domain results on a delay in the frequency domain. So here we see exactly that this term, which is the red term, it is exactly f2 of t exponential jst. As a result, we can write the integral I, which is an inverse Fourier transform of f1 convolution f2. So I can make f2 outside the integral because I am integrating now with respect to s. So I will multiply now by 2 pi, and I will divide by minus 1 over 2 pi. f1 of s exponential jst dt. And the blue quantity, or the blue expression here, it is exactly the inverse Fourier transform of f1. As a result, we conclude that f1 convolution f2 has an inverse Fourier transform equal to 2 pi f1 f2, or the Fourier transform of f1 times f2, it is 1 over 2 pi, the Fourier transform of f1 convolution f2.